recording.
So,
Okay, we're kind of talking about material science stuff today, and there's just this thing that I popped into my head the other day. I was watching Star Trek, or I've been watching Star Trek, and do you remember the episode of Voyager where they have like the that armor plating that comes up?
yeah,
Like they,
like Janeway comes
yeah,
back from the future, and
yeah.
and and
Yeah, there's like two Janeways and the Borg are doing something. I
yeah,
forgot. I'm dating myself. It's been a long time.
yeah,
Like I
yeah.
watched that episode when it aired for everybody here. Um, but they called it Duranium, I think. And I was like, at the time, I was always like, what does that, like, what is that? How do you, uh, how do you come up with materials and what properties would that material have?
But I mean,
That,
this is what Star Trek does. Like, if you're gonna
yeah,
call and find fault with duranium, like they have tritanium, they've got dilithium,
yeah.
they've got all of these made up materials, and
Well,
they kind of have to tell the story because it's obvious that the other materials that
yeah,
we know today wouldn't hold up.
that's true. They're making magic science metal. I understand that, but it's like,
What's wrong with uranium that like tritanium
I
is?
don't, because it's metal that appears from nowhere. It's like I could buy a shield, but like the materializing. I mean, they had their stupid. They're not stupid. They had replicators. They were in a post-scarcity society, which is also something that I took issue with. But that's another topic. Maybe if we have a conversation on economics, we can talk about post scarcity implications of
Yeah.
replicators. Um, but we're talking about metals today.
Yeah, so we should probably get on to that.
Yeah,
We should probably get on to that. So metals, real ones,
real metals.
real ones, not fake ones like duranium or unobtainium or what
Yeah,
have you that they make up in movies. Um, we're going to talk about real metals. But before we get into all of that, we're going to first take this first video and we're going to talk about what material, like a little bit about material properties in general, so that we can kind of relate what those material properties that we see in metal are.
yeah,
So, we're going to talk about stress and strain.
yeah. These are two concepts that we need to, I think, understand broadly before we can really have a conversation about material properties in a helpful way as it applies to things like steel or iron or composites or any other material that we
Yeah.
want to build something out of. We need to kind of understand like some basic properties and some basic terminology.
Like how to analyze what material properties are. Like,
Yeah,
what is metal? Like, you don't really like unless you have some sort of framework for discussing it uh, on its own,
yeah,
or framework for discussing it in relation to other materials, you're not going to have a very productive discussion about it. Like, I know it when I see it is kind of where you will wind
where
up.
you end up. Yeah,
Uh,
which is not where you want to be.
that's not where you want to be.
Yeah,
So when we talk about material properties, we start talking about things like how does the material behave? Is it brittle?
yeah. What does brittle mean in like because like we have the like when we're talking about material properties, stress, strain, brittleness, ductility, strength, all of these words are used in kind of common language.
Yeah,
But when we're talking about material properties, they mean very specific things under like specific circumstances. So
but they're often not far off
they're
from what
not
we
far
think
off.
about them.
The
And you're probably familiar with brittle.
brittle,
You
yeah,
know, you probably have had peanut brittle unless you're allergic, or some
yeah,
sort of nut brittle. Um, and when you think about brittle and what it is, or when you use it in normal English, it's basically what it means. It has a tendency to fall to pieces, like to
yeah,
crack
yeah,
and fracture
and shatter.
and shatter rather than stretch or give or be
Yeah,
compliant
or deflect, or yeah,
or be ductile. because the thing is the opposite of brittle is ductile,
ductile.
and you're probably not as used to that term or hearing that term. You may have heard it, but ductile just means that it has the ability to stretch,
it's
deform before fracturing.
before fracturing. And so it's the brittleness and ductility. They kind of are opposite ends of a spectrum. In a
Yeah,
way.
like there isn't something that is distinctly brittle or distinctly
distinctly-
ductile. Like at some point, like even the most brittle material will stretch a little tiny bit,
Yeah.
and even the most ductile material will fracture.
Yeah, and it's really kind of like, so it's a spectrum of two characteristics.
So we're talking, and we're going to have a lot of these sort of things where we'll have like a positive and negative end on an axis of information when we're talking about material properties.
Yeah.
So when we talk about what is brittle, what is ductile, like really it's like, since it's on a spectrum, we kind of have to have some way of charting where it is on the spectrum.
Right.
And what we use to answer these questions for brittle and versus ductile is what's called the stress strain curve. And it helps us do a number of things to understand and predict material behaviors. So if you go to the next slide, we'll define it here. It's the relationship between the magnitude of applied stress on the material and the resulting strain or elongation. So here we go. Like everybody knows, like has heard the term stress and strain.
Yeah.
Another one where we got, they're not interchangeable
Yeah.
like they are when we're talking in English.
Yeah. Like our common vernacular does not apply to these two terms when we're talking about material properties.
They're related,
They're related.
but the difference is in common English, you know, unless you're being very precise about your language, because they do actually mean exactly what they say.
Yeah.
But in common English, you know, like
These are often interchanged.
they're often interchanged. They're different. One is the result of the other.
Yeah.
So stress is an applied load.
Yeah. So me pressing down on this table, I'm applying stress to the table.
Yes. Strain is how much that table is deflecting or deforming
Because of
the load that you've got there. And these properties actually have units involved in them. So it's important to keep that in mind. You know, if you're thinking right now, we're you know, like we're in like the first week of the quarter here. We are all of a sudden going to go today and go through material that's going to go down to the atomic level of metals and then bring it back up, talk about how you put it in an oven to change its material properties. We are applying on you, the student, stress. I think you probably feel that. And that load, that stress that we are placing upon you, you will then strain. You will stretch yourself to accommodate that load, or you'll crack.
Yeah.
To bring it back.
It's not the intention.
It's not the intention. No, you all are ductile enough. You can handle this load.
Yeah.
But we're going to put it in terms so that you can understand that. So the stress is the load that we're placing upon you. The strain is the stretching you do, the strengthening yourself, the sort of resolve and work that you do to bear that load.
And so again, when it comes to materials, the strain is the result of a stress placed on an object or material.
One causes the other. Stress causes strain.
And strain is going to is exhibited in the material by deflection, and then ultimately, like if you apply enough strain, or if a material experiences enough strain, it will begin to fail in predictable ways.
Yeah.
Or what we ideally want to do is find the way to predict how, when, and why
Yeah.
that material fails under a particular load.
Exactly. Yeah. So, stress itself, when we are showing it in an equation, we use the Greek symbol sigma. That little,
The little O with the like curly Q coming off the top.
yeah, curly Q on it,
Or-
and it is an applied force.
Yeah.
It is newtons, but it's an applied force over a given area.
Yeah.
The area is important so that we can get materials to behave the same.
Yeah.
So like,
And we have something to compare materials against. We
Yeah.
can make comparative analysis of different materials.
so if we go back to the table here, Mike was pressing on, it is made out of one thing. But it isn't just that it's made out of one thing, it's made out of this plywood that is 1.5 inches thick,
Yeah.
right? Well, what if we are just looking about plywood in general, regardless of thickness? We need to do that over a cross-sectional area in order to make apples to apples comparisons.
Yeah. And this is one of the things that people can get a little tripped up on when you're first looking at this subject matter, is remembering that when we're talking about stress and strains, we're always concerned with like a force applied over a given area.
Yeah.
And the reason for that is because we need to be able to compare dissimilar materials to each other versus their performance under different types of loads.
Yeah.
And the easiest way that you do that is you say X amount of force over a given amount of surface area or
Yeah.
area.
So, and we'll get to this point, like
Yeah.
that, like if you're going to pick between, do I make this part out of plastic, do I make this part out of metal, do I make this part out of ceramic, you're going to look at what like goes into that.
Yeah.
And, like what are the loads and how much are they, and what makes the most amount of sense here, and you're going to be looking not just at stress and strain, but you're going to be looking at like heat resistance and
Yeah.
any other things
Because
that enter into that.
material properties change given different environmental factors, and that's also something that we get concerned with when we're looking at a machine and looking at like the materials that it's made out of. Very often can indicate, especially if you have a machine where suddenly you see like everything else might be made out of mild steel, but there's a component on there that's suddenly made out of ceramic.
Yeah.
And that would be an indicator. Like that would be done for a specific reason. The reasons could be, there's a multitude of reasons that might happen, but like understanding the material properties of ceramics versus steel or iron helps you intuit why and what is likely to happen from a maintenance perspective on those things.
Yeah.
So.
Yeah, absolutely. And so you'll see how that applies
Yeah.
when you actually start seeing the graphs here. The important thing here is to understand it's a pressure. So stress is actually like PSI or KSI,
Yeah.
which is kilopounds per square inch, which makes no sense because it's mixing metaphors.
Yeah.
But you'll also see pascals, which are Newton meters squared.
Yeah.
Or you'll see, because as we talked about before, pascals are actually like
They're very
newtons are very small, so pascals are very small.
And
And especially when you spread it out over a square meter.
versus like a square foot, like a pascal is a very small amount of force.
Yeah. So, so when we're talking about pascals, you'll often see things like megapascals, gigapascals.
Yeah.
You're not really, unless you're
doing something down at like
a nanoscale,
like will you deal with individual pascals
or millipascals.
or millipascals? Like it's,
If you're dealing with picopascals, I think you'd probably be dealing with like, how much does this atom
way.
Way.
Yeah, and like you're getting down to and the reason we're talking about this is to understand that like the the metric units that we're using to describe these forces, like the base unit is very small, so it is perfectly normal to see things like in like the range of like putting a cup down on your table or something like that. That might be in the range of like kilo or megapascals.
Yeah.
Like it's
Like kilopascals, pascals, gigapascals. Like if somebody says that like this is gigapascals, there's kind of a professional responsibility that you don't have your gasters flabbed
yeah.
by hearing that, because it's not as impressive as it sounds when we think
Yeah.
about normal context of.
It's very different than somebody saying we're putting something under like 1,000,000 pounds per square inch
Yeah.
versus like a gigapascal,
Yeah.
uh, like or 1 billion newtons per meter.
Yeah.
Like the 1,000,000 pounds per square inch is way bigger.
Yeah.
Is a way more intense force than 1 billion pascals over a meter.
Yes. So keep that in mind when you're looking at these things. But it's either going to be a metric or an imperial measure. Um, strain, on the other hand, is a unitless unit. Unitless because the units themselves cancel out. So it's epsilon, lowercase epsilon.
Yep.
Little,
The little e, the little fancy e.
fancy e. And strain is the length of elongation in millimeters, inches, whatever it is.
If you're working in psi,
Yeah.
your strain is in inches,
Yeah.
right?
You keep the unit system
keep
the
it the
same.
same, yeah.
If you're working in qubits, I have no idea what you're doing.
Yeah, just stop.
But yeah. But it's a length of measure, right? And then we divide that by the original length of the material. So the resulting unit is millimeters over millimeters or inches over inches, which makes no sense because those actually cancel each other out.
Right.
Another way to consider it is that it's kind of a percentage elongation.
Yeah.
You can basically express it as a percentage elongation.
Yeah, so it would be like because it's your original length versus your new length after the stress has been applied.
Yeah, so when you divide those two numbers out, you get a ratio
You get a ratio
that represents a percentage.
Yeah, and so you might have a strain result that is 1%, but you also might have a strain result that's 200%,
Yeah.
depending on the material.
And 200% means that it doubled in length before it broke.
yeah,
Yeah. So then what we do is we put those two things, stress and strain, on two axes of a chart. And we get something that looks like this. And this is what, this is just kind of a generalized one. And we're going to go through the terminology that's on here. So you've got stress going in the Y direction. You've got strain going in the X direction. And what we're doing is we're seeing how much it stresses given any load. So as the load rises, you'll see there's this linear portion of that where it goes up in a straight line.
yeah. It's very like as stress increases, the strain also increases in this very predictable linear relationship.
Yeah, and that's true for the vast majority of materials has this linear
relationship initially.
relationship, at least things that we consider normal solids,
Yeah.
Newtonian solids,
like a ceramic or this table
or metal or plastic or what
whatever.
have you.
Yeah.
When we're talking about solid materials, most of them will have this linear region right here. And, you know, any line has a slope to it, a rise over the run.
Right.
And that rise over the run is when we calculate out that ratio, we would call that Young's modulus. And basically, a steep line means that the material is extremely rigid.
Yep.
whereas a more shallow
Line
line
implies ductility,
implies,
or use the correct term.
a flexible material.
Flexible material. Flexibility. Sorry.
Um,
Not ductility. Flexibility and ductility are different things.
yeah, because they're related.
They're related, but like they are technically, they mean different things.
Right. So when we really see ductile happening here on this curve is we reach a point where the linear relationship breaks down.
Yeah.
And this is where the material is beginning to fail. It's beginning to stretch more for less load that we apply it to it.
Yeah.
And so during that phase, we can reliably count on the material kind of operating in this nice, neat, linear pattern in the beginning, and then it reaches this yield strength and it starts to yield.
Yeah. So what we mean here is like it starts to deform.
It starts to deform. It starts to deform permanently.
Yeah.
And it's important to understand that like when it's in that linear side of things, it's what's called elastic deformation.
Right.
In other words, if we take that load off of it, it will snap back into place.
Yeah.
Like elastic.
Yeah. And so like it returns to its original shape is
Yeah.
essentially what you can think of that.
Yeah.
Like as long as we're on this Young's modulus slope, somewhere on there, the moment we let the strain off or the stress off, excuse me, we return to our original length or original shape, whatever.
Yeah. And then beyond that yield strength, though, we are doing permanent deformation.
Yeah. Or plastic deformation.
Plastic deformation, yes. So plastic is actually a property that's on this same like axis sort of thing. You've got elastic
And plastic.
and plastic, and plastic just means that it does not go back, whereas elastic does go back.
Yeah.
And so plastic is not really the technical term for what we broadly consider as plastics, but everybody calls them that, and it's because they are formed essentially and used a lot of times to deform permanently.
Yeah.
Like the way that we mold plastics is through a permanent deformation of that material.
Yeah. And so like plastics are like a category of materials that kind of all fall under this same kind of.
The technical word for it is polymers, and we'll get to that another day. We're not putting that stress on you this week.
No.
So that plastic deformation region is broken up into two distinct parts, where you have the strain hardening part, where it's still able to handle more stress.
Yeah.
In order, and it, although it's elongating at a greater rate, you see that hump going over,
Yeah.
and then it reaches that peak of that hump, which is called the ultimate strength.
Yeah.
Which is higher than the yield strength. And then you get necking,
Yeah.
and necking is where it's essentially losing that. And the reason why it's called necking is that when it's in this stage, if you've ever pulled apart a piece of plastic and noticed it get narrower in the middle, it's necking.
Yeah.
At that point. And that's one of the reasons why it's going to that. Once it starts reducing that cross-sectional area that we calculate that over,
Yeah.
all of a sudden you're concentrating the stress in that area.
More and more and more. And
more and more and more. And so it is able to take less and less strength as a result of that.
And as you continue, and because like the stress is being concentrated in a smaller cross-sectional area, this behavior of elongating and deforming accelerates as you go down this curve.
Yes.
Right. So.
And then, you've got a nice red X there when it breaks.
Yeah. And so.
So technically when it breaks, it is a precipitous drop down to zero.
Yeah. We are now in two pieces.
We're in two pieces at fracture there.
Yeah.
So what we look at when we're trying to describe whether something is brittle or ductile is really like that slope of the of that. But like really, when we talk about ductile versus brittle, we're talking about failure modes.
Yeah.
So we really kind of look at what's happening after we reach yield strength
Yeah.
to really describe that.
Yeah. And so, um, a material that is brittle might be able to take a great deal of strain up to its yield point.
A great deal of stress.
Stress, excuse me, up to its yield point, and then like a brittle material would have a very short strain hardening portion of this curve.
Yeah, you would barely even notice it. You
Yeah.
just look a little blip, and then bam,
then you immediately fracture.
then you immediately fracture. Whereas a ductile material would look a lot more like
This-
what we see up here.
Yeah, where we have this very kind of elongated hump after yield, and then eventually it fractures at some point much farther away from the yield strength.
Now that strain hardening region, what's happening during that is that it's actually getting a little stronger because of the strain that we're doing, because that's a form of work hardening,
Yeah,
which we'll get into
we'll talk about.
later.
Yeah,
But essentially what's happening is that you're creating dislocations that actually make the material stronger, and that's why it continues to rise after the yield strength and doesn't just
fall off a cliff.
fall off a cliff.
Yeah. Yeah.
So, all right, let's go on to the next slide here. So this is just a description of what you saw in the previous slide. It's here for you when you need it.
Yeah.
So let's talk about how we test these things. Usually we play around with dog bones.
Yeah.
These are what called dog bones.
This is a standardized test article that we put in a machine.
We put it in a machine and pull it apart.
Yeah.
This is for tensile testing. So
Yeah.
tension,
We put
testing and tension.
yeah. We're
Pulling apart.
pulling stuff apart.
You can also do compression testing. You can do flexural testing. There's multiple.
There's
testing
multiple mechanical ways that we test materials.
And so when we do this, we basically pull it apart and we can measure the original length versus the elongated length. Now, we want to do that over not just the region where it's actually stretching the most. We want to do it over an area, so we measure the original length. And we want to make sure that that wherever it fractures is inside that region when we're testing it. So
Yeah.
as you can see, the dog bone is really designed to basically ensure that the fracture happens between 2 points.
Yeah, and it's to
So
make
it's
it.
narrowed down in there, and so therefore the cross-sectional area is less.
Yeah.
And so that cross-sectional area, when we're talking about doing testing, is the width and thickness of this dog bone.
Yeah. And these are standardized, this is a standardized shape.
Yeah.
Like when you're doing this material, when these types of stress strain curves that we were looking at are generated based on materials, like it's done off in an article that's to like a standardized set of dimensions.
Yeah, a standardized testing protocol.
Yeah. It's the only way it makes these graphs comparable.
Yes, because you need to do it exactly the same on all materials that you want to compare with one another. So
Yeah.
all of these are, ASTM is the standardizing body for that.
Yeah.
And what they do is they'll measure the original length, they'll measure the length, the end length, and oftentimes they're capturing that elongation in real time to get us a stress strain curve. So you'll use an extensometer that just measures it as it's stressing, like it is actually clamping on at that original length in those spots, and then it measures it as it goes out like a dial indicator.
Yeah, so just to make this really blatant, like when these go into the machine grabs onto these thicker portions here, and then it pulls this thing apart from opposite directions until it fails. And during the entire test, they're capturing live data from an extensometer that is essentially measuring how quickly it is changing shape in real time.
Yeah, exactly. And so you can do this at home if you want, just like really unscientifically, but you could, and like just to kind of get an idea of it, you can cut open, cut a plastic bag up
Yeah.
into a dog bone shape like this,
Yeah.
pull on both ends of it, and measure it and see
Yeah.
where it winds up in the end result, and
then-
you can kind of see a little bit what's going on
Yeah.
there with that.
You can also do that, like you can do like a plastic bag and a paper bag, cut out, like make them the same dimensions and stuff.
Yeah.
Pull them apart, and you'll see like they behave differently.
Yeah. That's what material testing is.
Yeah.
So basically, we do that multiple times. We want
Yeah.
essentially a sort of median. We
Yeah.
need a sample size. We need the median characteristics, not the outliers.
And for the well-documented materials, like this is done thousands of times.
Yeah.
Across like, and we get them. These material, like we get samples of materials from multiple manufacturers to come together and do this type of testing. So
Yeah.
like this, like, so that we guarantee that like basically the graphs that get published are as accurate as possible.
Right.
So we can use them for engineering applications.
Yeah, and if you've got a copy of the machinery's handbook,
yeah.
which is a good thing to have if you
Yeah.
don't have it, like it has tables and tables of materials and their Young's
Yeah.
modulus
Yeah, I think that,
and their yield point.
yeah.
Um,
And I think the thing here the reason we're bringing this particular thing up is that like these are all solved problems for
Yeah.
the most part for any material that you guys are going to realistically interact with.
yeah,
Like if you need to know this stuff, you don't go and do this testing yourself.
No.
You go look up the
you look it up
results.
on a chart, and
Yeah.
like if it needs to be a certified material, you have a testing company do that
Yeah.
according to ASTM standards.
Yeah.
I mean, unless it's tritanium
Or unless it's
Duranium.
Yeah. If you're making magic
if you're
science metal,
inventing a magic science metal, you probably should do some testing on that and
Yeah.
see whether or not you're going to have a brittle failure when shot at by the Borg.
yeah. Moving on.
Moving on. Stress materials.
Yeah.
So just to get more into Young's modulus. Young's modulus is what allows us to compare items together.
Yeah.
Because we remain in this linear, like if we remain in the safe region of this linear region, the material will snap back to its original thing. It's not actually being damaged by the loads that we're applying to it, which is what you want to make sure that you're staying within that linear region. So you need to make sure that you're well below the yield strength of whatever application that you're doing. And because we keep this in pascals and strain, two things that are the same regardless of the dimensions and geometry of the material, we can compare different materials with one another.
Yeah.
Because we're removing the variables of geometry.
Yeah.
The thing is that you can make a piece of plastic, if you make it thick enough,
Yeah.
bear the same load as a piece of steel.
Yeah. And you can make a piece of steel fail by making it smaller than another, like making it small enough. Like you can
Yeah.
make, I mean, for example, you can get steel foil
Yeah.
that folds like paper
And tears.
and tears
Yeah.
because the cross section is so thin.
Yeah. So so this is what allows us to compare material, and then you can just kind of adjust your geometry to fit
Your application.
your application. So, and it should tell you, in addition to that, it should tell you, like, if you're going to put it under this load, exactly how much it's going to deform.
Yeah.
So, like,
That's where the predictability comes into play.
Yeah.
And that's why we get like these materials go through such extensive testing, is because we want to say with a high degree of confidence, like if you put it under this much stress,
yeah.
given this cross-sectional area, it will behave like this.
Yeah, so let's say I want to hang, for whatever god-awful reason, a car from the ceiling in the 5th lab.
Sure.
I would need to use the Young's modulus for the steel cabling that I'm using
Yep.
to determine not just like how many cables I'm going to need, what thickness of cables. You would be able to
Yeah.
determine that from this. But you would also be able to calculate, if I cut the length without having it under tension,
Right.
how much is it going to droop
Yeah, exactly.
as a result of the the load, the stress
Yes.
that that car is placing on it.
Yeah. Um, which, depending on the type, like you may run into machines where something like that is happening, where like the load that's placed onto the material is intended to deform it in a certain way,
Yeah.
so that the the machine or the piece of equipment falls into maybe a proper alignment, or that it's applying a certain amount of load to another part of the system. Like,
And like this is a real thing that could
Yeah.
you could have to deal
Yeah.
with. You know, like we almost had to deal with this when we built this building.
yeah, yeah.
Well,
Well,
we wanted to deal with this problem.
Yeah, we
At the time when we were building this building,
Yeah.
they had a surplus Saturn V first stage,
yes,
and
that we
We're
could
like-
have acquired for very little money.
it would only have cost us what it took to ship it here.
Yeah.
It was essentially free otherwise.
Yeah.
And I was like, we got a nice long space.
Yeah, we
We
could.
dang that from the ceiling.
Yeah,
But no,
no, it didn't fly.
nobody wanted to have fun.
Yeah, I would have liked to have a Saturn V first stage.
Actually, no, it wasn't the first stage. I think it was the second stage.
Oh, Saturn V second stage. Okay, yeah.
Because I mean, the first stage.
Stage. Yeah, I was like,
I don't
Yeah.
think width-wise it would have fit.
Fit,
It might have fit lengthwise, but
yeah, I don't even think lengthwise it would have fit in the fifth lab.
yeah.
It
I
might,
think,
like
I think
if
it was
we
the
knocked
second
out the
stage.
bill, if we knocked out the wall to the NDT lab, maybe.
Maybe. Yeah.
Anyways, so Young's modulus. This is the thing that like this is the portion I think that we use to compare materials like
Yeah.
most often.
Most often.
Okay, linear. So linear elastic portion.
And you know, we've kind of
yield
gone
strength.
through all of these
Yeah.
things, so I'm going to kind of leave these here
Yeah.
as further descriptions as you're reviewing this
Yeah.
slide deck, because we've kind of been talking for a while here.
Yeah.
So just make sure that you're relating the descriptions to what's here on the screen.
On this graph. I think.
So here is an example of low carbon steel. So we
Yeah.
see this. We have a ductile failure mode here, but we also have a very
Steep, Young's,
like a high modulus,
Yeah.
high rigidity material
Yeah.
up until its yield point, but then it stretches
Yeah, and it stretches quite a lot.
quite a lot.
And you can also see that it also work hardens quite a lot because as it's deflecting, it continues to take more and more strain up to a certain period. And in the grand scheme of things, like the mild steel is not the strongest, doesn't have the highest absolute or ultimate strength
No.
material, but you can see that its ultimate strength is about 50% greater than its yield strength.
And when we talk about work hardening, why do you think they smack hammers on steel?
Yeah,
That's what it's doing.
yeah. And so like
Uh,
when you're cold forging material, right?
Yeah.
Like you are literally doing this to the material.
Yeah, you're introducing strain to keep it going. So and then so this is just kind of a visual example of again the brittle versus ductile. The big thing there, you know, they both have relatively
Steep Young's modulus.
but we're characterized a ductile failure will have a like higher or lower yield strength. It doesn't really matter, but like a really elongated failure mode where it's in the plastic region is really
Is
long.
really exaggerated on the
because
graph.
on that brittle one it's just failing and dropping to zero like super quickly.
Yeah, and so when you're looking at these graphs, typically it's not like you're going to get like an X on the failure point every single time, FYI.
Yeah,
It's
no,
just like when the line stops, that's where the fracture happened.
And when you're actually testing it on a machine, it will actually measure the drop to zero, and so
Yeah.
it'll just be a straight line down.
Yeah.
So that's pretty much stress and strain.
Yeah.
And we're going to spend a lot of time talking about like material composition as it relates to metals. We're going to focus a little bit on other things in the next video.
Yeah.
But we'll save that for the next video.
Yeah. So keep in mind what we're talking about with stress and strain for all of the discussions around materials and the different things that.
Yeah, it doesn't just apply to metals.
It applies to all materials that we build stuff out of.
Yeah.
So we'll see you guys in the next video.
See you in the next video.